Great, so welcome back. This is our third video about the Markov chains and hidden Markov models. So we are discussing stationary distributions and we end up with this slide here in the previous video. So let's talk a little bit more about this. So we were discussing how to compute these stationary distributions, but also important is to have a little bit of interpretation of what is a stationary distribution. So we can look at this graph here that will have the transition probabilities, and we can think about this. So imagine that we are doing a random walk. So basically we start in a certain state and we decide we're going to move to another state or stay in the same state according to those probabilities. So if we do that, we can start, for instance, here in sun state, and in certain way flip the coin and to decide you're going to stay here or move, and with probability 0.9 we should stay in the same state, with probability 0.1 we're going to change to the rain, and we continue to do that. So you can decide to stay in sun, and change to rain, and keeping doing that in a random walk according to those transition probabilities for a long period of time. And the question is, how much time we will spend in each state? And if you look here at those transition probabilities, it's going to be clear that we're going to stay in the sun state 3 times more than we stay in the rainy state, right? Because there is just 1.1 probability of transitioning from sun to rain, but there is the triple of that probability to transition from rain to sun. So we can expect that we're going to stay in the sunny state 3 times more than we're going to stay in the rainy state according to these probabilities. Of course, if it was like 0.5 here and 0.5 here, and also 0.5 here by consequence and a 0.5 here, you will say that the stationary distribution would be half and half for each state. So that is the interpretation that we can frequently think about it, and they're going to help us to understand all the properties about the Markov chains. Is that we're going to do a random walk, and during this random walk you're going to compute how much time we spent into each state, and at the end the amount of time that we spend in each state is going to be the probability of that state into the stationary distribution. Okay, and one important definition is if a Markov chain is irreducible or regular. So the idea here is that a chain is going to be irreducible if we can start in any state and we can reach any other state in the future with a probability that is greater than 0. So a little bit more formally, let's read what is here, right? It's saying that for every pair of states x and x prime, there is some time t in the future such that the probability of reaching x prime from x is greater than 0. So that probability cannot be 0. So basically what I'm saying is that, okay, if we start in a state x, it can be any state, right? And we start, jumping into the Markov chain, into the states. And at some time, it doesn't need to be the next one. It doesn't need to be 10 or 20. It can be 100, 1,000, 1 million in the future. I will be able to reach any other state of the chain with a probability that's greater than 0. Okay, let's take a look at what is one reducible Markov chain. So the reducible Markov chain, it is not irreducible, so it means that we will not be able to reach the x prime state. So let's suppose that we start at state 1. And if we start at state 1, we can continue in the state 1, or we can go to the state 2. So far so good. In state 2 we can continue in state 2, we can come back to state 1, but we cannot reach the states 3 and 4. right? So it doesn't matter if we start with 1 or 2. It doesn't matter how much time we spend in this chain, we will not be able to reach states 3 and 4. Something similar happens with state 3. If we start in state 3, we will transition to states 2 or 1 or to the state 4. And we will never come back to state 3. So it's also possible, right? So this x prime can be x2, and we will not be able to reach state 3 again. The same thing happens to the state 4. If we start in state 4, we will continue at 4, and we will never be able to reach states 3, 2, and 1, and we will continue to be there. So this chain here is what we call the reducible Markov chain. And why this definition is important? So I'm going to see that these Markov chains that we are working with discrete states, they all have at least one stationary distribution. But in order to have one unique stationary distribution, we need that the chain to be irreducible. So what is going on here is actually very simple to explain. Is the fact that if we simulate this chain for a period of time that is long enough, what's going to happen with the stationary distribution? So it's going to be like this. So imagine that we start at 1 or 2. So we're going to jump from 1 to 2 and 2 to 1 and 1 to 2 and 2 to 1. So if we start with one of those states, our stationary distribution is going to be like this. It's going to be 0.5 for the state 1, it's going to be 0.5 for the state 2, because they jump between each other with 0.9 probability, so they're going to share the same amount of time in each one. But the probability to reach 3 and 4 are going to be 0. So this is the stationary distribution when we start in 1 and 2. When we start at 3, what's going to happen is that we can go to 1 or 2, or we can go to 4. If we go to 1 or 2, we'll have exactly this stationary distribution. But if we go to 4, what's going to happen? We're going to stay stuck in 4, and in this case, the probability for 1 and 2 and 3 is going to be 0, and going to be 1 for 4. So this is the stationary distribution with we starting in 3. It can be or this, depending on how we started. And if we start in 4, it's going to be like this guy here. So we have two stationary distributions, right? So, and it will depend on how we start the chain. So in order to have one unique, we need to be able to access all the states all the time. So we will never have this sort of split as we have here, that we get stuck in a part of the chain and we will never be able to reach the other states. If every state can reach every state after some time moving inside the Markov chain, that will guarantee that we only have one stationary distribution. So here is another example of one reducible Markov chain. So in this case here, it's just one single, so this entire thing here is one single state space where we have four possible states, 1, 2, 3, and 4, but there is no connection between states 1 and 2 and states 3 and 4. So if we start in state 1 or 2, our stationary distribution is going to be 0.5 and 0.5 and 0 and 0. So this is our stationary distribution. If we start in 3 or 4, it's going to be 0, 0, 0.5 or 0.5 because we will not be able to reach the top part of the state space. So one important practical result of this definition of reducible or regular chains is the fact that for many applications, we define what's going to be the Markov chain. So it's possible that who is designing the application will specify what are the states and what are the transition probabilities between the states. So, and for many of these applications, we are interested in a single stationary distribution. So this result is very important, is because as we design our transitional probabilities, we have to be careful to make every state reachable from any state. So we're going to guarantee that I have just one stationary distribution. And we're going to see this one example at the end of this part of the lecture, when we end with the Markov chains. That is the page rank algorithm, and we're going to see how they manipulated the chain in order to guarantee that you would have just one single stationary distribution. That was the page rank that is assigned to each web page. So another relevant question is that, let's suppose that we have one irreducible chain, and will this irreducible chain converge to the stationary distribution? And the answer may be no. It will depend on another property that's called aperiodicity. Let's take a look on the next slide. So, okay, let's take a look now at this definition of aperiodic Markov chains. So the general idea is that the Markov chain is aperiodic if it's possible to return to any state at any time. So I start in state X, at any time I can return to this state X. So a little bit more formally, let's look at here. So it says that there exists a time t such that for all state X and for all the times t prime that are larger or equal to t, it will be possible to return to the state X at this time t prime, given that I started at the state X with a probability larger than 0. So it cannot be 0. So it is a strange definition that it sounds much like the definition that we have just made for irreducible Markov chains, but it's actually different. So in order to better explain this, let's take a look at one example and see that if we can make it more concrete. So this example here is one irreducible but periodic Markov chain. So look at that, we are defining what is an aperiodic Markov chain. So this is a periodic Markov chain. So this property here will not hold. All right. So first, let's take a look and see if it really is an irreducible Markov chain. So we know that if it is irreducible, we can start from any state and reach at any other state in the future. So we can start in 1, and from 1 we can go to 2, and 2 to 3, and 3 to 4, and from 4 to 3 to 2 to 1. So there is this loop here. So it's very clear that we can start at any state and we're going to reach any other state. So it's clear that this is a irreducible Markov chain. So it means that it has a unique stationary distribution. But the point is, will we converge to this stationary distribution? And the answer in this case is no, because this chain is periodic. So let's try to understand what is this periodic chain. So let's suppose that we start, I'm going to make here a small table, hope that's going to fit here, that we have the time t, and these are the states that we can reach at time t, and let's suppose that is time 1, and I'm going to simulate this. Let's start with state 1, 2. Okay, so at time 1 we are at state 1. No issues. At time 2, what happens? Well, we have to transition to state 2, right? So we're going to be in state 2 at time 2. Okay, no problem. At time 3, well, at time 3, there are two possibilities. We can go from 2 to 3, all right? Or we can come back to 1. Okay, so it can be 1 or 3. All right, at time 4, what's going to happen? If you are at state 1, we must go to state 2. If we are at state 3, we can come back to state 2, but I have already written here, no problem. Or we can go to the state 4. All right. Time 5. At time 5, if I am in state 2, I can go to 1 or I can go to 3. And if I am at state 4, I must go to the state 3. But I have written here times 6. If I am state 1, I must go to 2. If I am at state 3, I can go to 2, have noted this, or I can go to 4. And this continues. So now you probably have realized that why we call this chain periodic. Because what is going on is that we are switching between the states. If you have an odd time t here, I will be in an odd state, like here, here, and here. If I have an even time, I will be in an even state. And we keep switching between the states and in a periodic way. So let's look again at the definition. What is the definition saying? To be an aperiodic Markov chain, we need to have the following. Let me erase it here to see if I can explain this better. But it's saying to us that exists a time t, so we can choose what's going to be the time t. I'm going to say that the time t is this guy here, for instance, such that for all state x and for all times t prime, so starting from time t, now for all the times t prime, starting from the time t, I will be able to reach the state x with a probability that is greater than 0. And that is not true. We can select any t that we want. It will not be able to reach, for instance, state 1 for all times t. So if we choose like here at 4, we can only reach state 1 at the 5, at the period 7, and so on. We can move this t to another place here, but that's continuing to be true because we continue to be able to access the state 1 only at the odd time steps. So the problem with periodic chains is that we keep switching between the set of states back and forth, and we do not allow us to converge to the stationary distribution. So just to be clear here, we have two definitions. One is the irreducible chain, that we can go from any state to any state, and we will guarantee that we have just one stationary distribution. And we have this notion of a periodic Markov chain. And when a periodic Markov chain, it avoids a chain that alternates between states without ever settling in a stationary distribution. Okay, one final slide about this is that even though we may have one irreducible and a periodic Markov chain, we know that it's going to converge to a single stationary distribution. Even though we have these two properties in the chain, the convergence can be very slow. So we can think in one very simple example where this happens is like this. Suppose that we have this epsilon here that are going to be the transition between state 1 to 2 and from state 2 to 1. But we can think that number will be very, very small. So if we simulate this chain and start doing a random walk in the chain, you're going to see that we're going to spend a lot of time. So suppose that we start at state 1, you're going to spend a lot of time in state 1 and hurriedly transitioning to state 2 and stay there for a long period of time. And again, going to take a longer time to transition back to the state 1, and it keeps like this. So even though it will converge, we'll have to simulate this chain for a very long period of time in order to get the convergence. So again, it's guaranteed that it will converge. It will converge to a single stationary distribution that in this case is going to be 0.5 and 0.5 for the states 1 and 2, but it may take quite a bit of time if we select one epsilon that is extremely small. So there are a few applications of Markov chains that we can talk about. One of them that we're going to see in future lectures is called the Markov chain Monte Carlo method. It's a very powerful approximate inference algorithms that we're going to discuss in the sampling inference algorithms that we're going to have in a future lecture. This is really powerful techniques, and many softwares that use Bayesian inference use these techniques in order to compute the answer for probabilistic queries. One example of these softwares is called STAN. It's very popular in the statistics community. Another example is the LZMA algorithm, that is a compression algorithm that incorporates Markov chains into the well-known Lempel-Zipf algorithm. So this new algorithm is called Lempel-Zipf Markov, and it is used by 7-Zip. And maybe one of the most well-known applications for Markov chains is the PageRank algorithm that is used, or at least it was used by Google when they started, and is a direct application of Markov chains. So let's discuss this PageRank algorithm a little bit in more details, because we're going to use this as one example that I'm going to develop in the tutorials. So let's think a little bit how it works. I'm going to open a new blank page here just to have a little bit more space to write. So the problem that Google solved is the following. So every time that we do a search in Google, we type a sequence of words and we start the search. What Google does is it has a very efficient indexing structure that it can retrieve all the pages that have the words that we typed in the search query. But of course, you're gonna have like millions of different pages about that words, and Google must order the pages in terms of relevance. So the most important pages should come first, and that is the important part of the algorithm. So there are two parts. One is indexing and retrieving everything that has a certain query. The other part is, that is the most important of everything, is how we order those web pages. So we present to the user the pages that are the most relevant first. So this is the PageRank algorithm. It's basically an algorithm that associates one number to each web page that was retrieved, and this number is used to sort the pages and present the most relevant first. So what we're going to do is to model the web using a graph. So we can imagine that we have a web page here A, and we have other pages like B, C, D, and so on. And the central idea is that the relevance of a page is proportional to the number of edges that are incoming in that page, right? So if you are one authority in a certain subject, probably several other web pages are pointing to you saying, okay, if you want to know more about this subject, you should go to this web page. But the problem of this model is that it's very simple to fool it. So we can, for instance, create several web pages. So we have here one page E that has no relevance, but we want to make it appear it's being very relevant. So we create several other fake pages here that they link to several other pages, but also to this page E here. So it's going to be several other ones pointing here. So the same persons that created the page E, they also created the other web pages that are pointing to E. So if we use as PageRank the incoming degree of the node, so E is going to be more relevant than A. And the central idea of PageRank is to make this approach more reliable, more robust, by creating a Markov chain and simulating this chain in order to compute the stationary distribution, and the final result is going to be the stationary distribution. So why this idea is good is the fact that if we consider this as a state diagram, right? So, or a piece of the state diagram. So the importance of A is going to be small because all those pages here that were created to increase the importance of E will not be accessible. So if we simulate this chain, there will be no way to get here in order to transition to E. So the amount of time that we're going to spend in E is going to be very small because we cannot access all those small pages here that were created to inflate the importance of E. Okay, so let me just erase this part here in order to make a larger graph. And so let's suppose that we have A, B, C, D, and another one here that's going to be, oh, I have already D here, so that's going to be E and F, and so just trying to make a slightly larger graph. So how is the idea of page rank? So the idea is actually very simple. So let's take the node C here as example. So we needed to associate the transition probabilities to this graph. And the idea is that I'm going to associate to each page a transition probability to another page that is a number that is alpha over K, in this case C. And Kc is the outgoing degree of C. And alpha is a parameter that is frequently set to 0.85. So I'm going to take 0.85, and I'm going to divide it by 3. 0.85, and I'm going to divide it by 3. I'm going to be clear why you're going to doing this, right? And I'm going to do this for all the pages that we have in the graph. So let's suppose that A has two going ways, one back here and another one going to F here. So I'm going to be 0.85 over 2 and 0.85 over 2 here. And we continue doing this to all the hyperlinks that we have in the web page. So we're going to create this large graph here, and we want to simulate a Markov chain and compute what's going to be the stationary distribution. But one problem with this graph, the way that we are designing here, is that it doesn't have one unique distribution. And probably you know that, right? Because it is not irreducible. So this is a reducible Markov chain. So what's going to happen is that we can get into a certain states like E and never leave E because E has no hyperlink in there. So every time that we visit E, we stay stuck in there and never leaves there. So that is a problem, and the way that they solved the problem was to assign a probability between one page and every other page. And the way they did that was to assign the probability that is 1 minus alpha over n. So in this case here, this 1 minus alpha is going to be 0.15, and we have 0.15 divided by the n web page that we have in the graph. So we're going to be here, like you're going to point from C to B, and this is going to have a weight that is 0.15 over 1, 2, 3, 4, 5, 6 pages that I have in the graph. And I'm going to do this to every page. So now I'm going to make our chain regular, right, or irreducible, because now we can reach any page from any page. There will be just a small technical detail here, is that there will be one link here, they call these phantom links, if I remember correctly, there will be one of those from C to C, that's going to be 0.15 over 6. There will be another one here that comes from C and goes to E. So actually here you're going to have a sum, it's like it having just one transition here, that's going to be the 0.85 over 3 plus the 0.15 over 6, and so on. So that's going to happen from C to every web page, and from also every other web page to every other web page. So A again will have all these links that connect A to every web page that we have in the graph. And so it should be clear that if we sum all the probabilities, right? So all the transition probabilities that are coming from one node to every other node, it must sum to 1. But that happens here because we have this term here, right? And we have this term here. And if we sum them together, we will have 1 probability. That is also very good. Okay, so they did this and they simulated the chain. So if you look at the paper from PageRank, the algorithm is the meaning forward algorithm, exactly the meaning forward algorithm with the Markov chain set as this way. As I was explaining before, and I'm going to mention this again, see how they manipulated the chain in order to make one chain that is irreducible. So initially they have one reducible chain, but they realized that this reducible chain would not have a single stationary distribution, and that was bad because having a single stationary distribution means that when we end the computation, we will know how to rank the pages. If you have more than one stationary distribution, we have more than one way of ranking the pages, so that is bad. So that is a good result. So they manipulated how they defined the chain by introducing those phantom links, so they make the chain irreducible. That is one interesting aspect of this model, and that happens a lot. In several applications, we define the chain, and as we define the chain, we can make it with the properties that we desire. Finally, just mentioning that alpha is a parameter. According to the paper 0.85, it was a common choice. So basically, it is splitting how much weight you're gonna give us. We're gonna give to the links, and how much weight you're gonna give to the phantom links. So if we choose that alpha is going to be 0.85, it means that 85% of the importance will be given to the regular links, and 1 minus alpha is going to be 0.15, and just 15% of the weight is going to be given to the phantom links. It's important that when we sum these two quantities here, we get 1, that is the probability of being in a certain state and going to all the other states. So just to finish, this is one figure that I got from Wikipedia, and we are going to reproduce these computations using the meaning forward algorithm. So yeah, just to illustrate that we have this web page here that it looks like is a huge authority for the topic, and we can see that it's a lot more important than this guy here, that even though it is important, it is less important because it is being pointed by several small pages that have very little importance. So they have their own very small page ranks. And we can see that this page here, because it is linked by this page, it has a very large page rank, even though it's not linked by any other page in the graph. So basically meaning that if you are linked by one authority, you have a large page rank value. All right, that is all for this video, and that's all for Markov chains too. We will come back to the topic of Markov chains when we discuss the Monte Carlo Markov chain algorithms in sampling. For now, let's switch to hidden Markov models in the next video. So see you soon.